Good day, my name is Oscar Liss, and today I'm going to be doing a presentation into the automation of ASPeCt ship-based observations. So, starting with the introduction, it's going to be broken up into three parts: the subject of the research, the project scope, and the significance of the research. The annual growth and retreat of sea ice in Antarctica is well established to be one of the biggest seasonal changes on Earth. The ASPeCt team, who do research into sea ice, specifically in the marginal ice zone, which is the boundary between open ocean and the hard pack ice, do observations from the ASPeCt as shown in the figure below. The project scope can be broken up into its aim and its objectives. The aim of the project is to develop an automated Python program to analyze sea ice in the marginal ice zone within Antarctica according to its form, temperature, diameter, and concentration. The first of the four objectives is to understand the formation of sea ice in Antarctica through analyzing existing literature. The next is to compare and extract the valuable findings from past projects to further develop the automation of ship-based observations. The third is broken up into two parts. Firstly, to calculate the sea ice concentration, the flow type classification, and the flow sizes according to visual and thermal imagery, and then to log the data and visualize the results for ASPeCt to allow for remote research, and finally to achieve the course level objectives. Sea ice in Antarctica makes up for the majority of sea ice on the planet. Building on this, sea ice is a key indicator of climate change. By understanding the characteristics of sea ice, one is able to track the changes in sea ice and infer future climate variability. Sea ice formation within the marginal ice zone is specific to Antarctica due to the intense nature of the Southern Ocean and the katabatic winds coming from the Arctic ice shelves. From here in the picture below, you can see the marginal ice zone in yellow and the hard pack ice in red. The figure next to it shows the formation of sea ice in the region. Sea ice can be analyzed using various techniques. Sea ice concentration is the ratio of sea ice to open water within a frame. Sea ice can also be classified by its thickness, its diameter, and by temperature. OpenCV is a package which can be used in Python for computer vision and image processing. The image on the left shows how a digital image is broken up into an array. Further research was done with the Handbook of Pattern Recognition and Computer Vision, developed by Chen and Zhang, and they specifically looked into active contours for sea ice detection. The first step in the process was the assessment of sea ice detection strategies. Through research in the literature review, it was found that infrared cameras can only be accurate to about 1 degree, where differences in sea ice vary by half a degree. Therefore, classification of sea ice by temperature was not reliable, and hence the thermal imagery would be turned into grayscale imagery and then run through the same pipeline as the visual imagery. Different methods of contouring were needed to be compared. The first method uses OpenCV's built-in packages of thresholding and contouring, while the second method uses the Handbook of Pattern Recognition and Computer Vision. The first method only took half a millisecond to execute, while the second method took 6.4 seconds to execute. Due to the difference in computational time, it was decided to go forward with the OpenCV packages. Sometimes there's not enough information in an image to successfully segment sea ice. Therefore, there was a need for the detection of outliers. Calculating the amount of pixels within a contour, you can detect the outliers by area using standard deviation. The outliers were neglected from the research and highlighted in red, and the inliers were highlighted in green. Now it came for the development of the pipeline. So the pre-processing functions of the pipeline are to calibrate the pixel to area ratio. So this means that the algorithm then knows the amount of pixels in an area related to a certain amount of square meterage in real life. Then thermal imagery had to be converted into grayscale videos. Then you take your pixel to area ratio, you input it, you input the path of the video to be analyzed, you retrieve the first frame to get your metadata, and then you can set your perspective transform. So you can scale it to make it bigger or smaller, you can shift it horizontally, and you can shift it vertically. This allows for a more universal control. The next is to set the threshold, and this will be the value at which the program chooses and distincts ice from open water. From here, you are now able to do your frame-by-frame analysis of the downloaded video. The flowchart below describes the execution of the frame-by-frame analysis. With each frame of the video analyzed, you can output your final video, you can log the results, and you can finally display and show all of the results. Okay, so moving on to the results and discussion. The work was completed in two different sections. Visual imagery comprises of 2 videos. Thermal imagery comprises of 3 videos. The graph on the top right you can see is the sea ice concentration changing per frame of the video, and on the bottom you can see the distribution of different types of ice, and they are categorized by either the number of flows in a category or the amount of summated area of the flows in a category. So in analyzing the first video, you can see that there are some inconsistencies in the sea ice concentration. These spike dips can be attributed to 3 main things. When flows are further away from the camera, the perspective transform has to account for this, and sometimes there's not enough resolution in an image, and therefore it's difficult for the contouring algorithm to segment these flows. Additionally, as you can see, there's wake from the ship. This increases noise in the image. And lastly, you can see that a video needs to have consistent light levels throughout the video so that the thresholding value stays consistent and is able to segment the flows. The next video is from the thermal imagery dataset. As you can see, the sea ice concentration is extremely close-knit, and therefore it is assumed that the contouring algorithm works extremely well for thermal imagery. This is because of 2 different things. The first one is that thermal imagery is less affected by low visibility and bad weather conditions. Additionally, the thermal imagery specifically taken here has a much smaller footprint, therefore the ice flows are easier to identify in the contouring algorithm. This video comes from the thermal dataset as well. This video was specifically chosen because it has a much lower sea ice concentration than the other videos. The algorithm performed as expected and was still able to differentiate between open water and sea ice, therefore showing that the algorithm can work with a wide variety of sea ice concentrations. The sizing calibration and time to execute had to be evaluated as well. The image below shows the setup that was made to test the sizing calibration. So the table above shows that there was a percentage error of 2% in going from the amount of pixels in a contour to the amount of area in real life. This percentage area is sufficiently small and can be moved forward with, whereas looking at the average time taken to analyze a frame, you can see that as the resolution increases, the time to analyze a frame also increases. I highly recommend you head over to my YouTube channel, linked above, where you can see all of the data capture with the full frames for all 5 videos. The limitations of the analysis need to be discussed. Image quality and resolution are important factors in the success of the contouring algorithm. As resolution increases and the use of a smaller footprint for the field of view of the camera is used, this significantly helps the contouring algorithm to detect ice flows, while image quality, specifically the consistency of the light throughout the whole video, is important for the thresholding value. The sizing of flows was done by calculating the amount of pixels within a flow and then having thresholds where if the amount of pixels within a flow went over a certain number, then it moved from frazzle to brash to pancake. However, ASPeCt categorize sea ice by thickness. Maris are currently working on a way to link diameter and area to thickness. And finally, the verification of the analysis should be done. This needs to be done using data that ASPeCt has analyzed with attached sea ice concentrations, and then cross-verify and see what tolerance there is in the algorithm. So, in conclusion, the analysis of 4,242 frames was done across 5 different videos, 2 of them being visual, 3 of them being thermal. This allowed and showed the plausibility of the sea ice concentration algorithm and the proof of concept for flow type distributions by size. Furthermore, the course objectives were achieved and lay an important roadmap to allow for the success of the project. The final findings are that the algorithm can be used as an analysis technique moving forward for ASPeCt for a remote research in the region. Finally, here are the references from the project.